We have two surfaces here, a hyperboloid h and a plane pi. Both of them are represented implicitly in the form of f of x, y, and z equals some constant c. How do we find all the points on the hyperboloid where its tangent plane is parallel to the plane pi? Here is a key fact that is going to help us solve this problem. If we know two planes are parallel, we know that their normal vectors must point in either the same or opposite direction, and so they must also be parallel to each other. The converse is also true. So let's get to it. As mentioned earlier, we have two implicit surfaces here. Let's label the implicit function for the hyperboloid as f. Now, think about what we really need to get what we are after. Do we really need the equation of the tangent plane to the hyperboloid? Not really, isn't it? Based on the key fact that I just brought up, knowing the normal vector to the tangent plane to h and also the normal vector to the plane pi would be good enough. What we can do is to get the desired points by relating the two normal vectors instead of the equations of the two planes. Getting these two normal vectors are very easy. For the normal vector to the tangent plane to h, we use the gradient of f. The three first partials of f are 2x, 8y, and negative 2z. Evaluating all of them at a tangency point p0, we get the I, j, and k components of the gradient vector at p0. Now for the plane pi, it's even easier. We can read off the components of the normal vector to the plane pi from its equation. As a reminder, the coefficients of the x, y, and z terms in the implicit function for a surface matches exactly the components of its normal vector. So here we have the normal vector to pi. Let's call it vector n sub pi. Now, applying the key fact to our two planes, we have the gradient of f parallel to the vector n sub pi. That means we can express the gradient of f at p0 as some scalar multiple of the vector n sub pi. This is where the only unknown for the problem gets into our way. The scalar multiple lambda is something that we are going to figure out, which will lead us to the points we're after. But we don't know how yet. Now, plug in the two normal vectors. We get these three equations by equating the vector components on both sides. After simplification, these equations form a parametric representation of the points that we're interested. Let's label them using an empty square. But since lambda is an unknown, it could be any real number, and we have infinitely many points. That doesn't make any sense. The reason is that p0 is just any point in space at the moment. We haven't yet imposed the constraint that p0 is a point on the hyperboloid h. Put it another way, the parametric equation for the points of interest must satisfy the equation of the hyperboloid h. By enforcing this requirement, we will get an equation in lambda to solve. So now we know how to sort out the unknown lambda. So let's plug the parametric equation into the equation of h. Expand the squares. Clean up the left-hand side. We have lambda square equals 4. That is, we get two possible values for lambda, 2 and negative 2. Each of these two lambdas gives us a unique point on the hyperboloid h where its tangent plane is parallel to the plane pi. All right, problem solved. I hope you enjoy the video, and I'll see you in the next one.